Hello everyone, and welcome to our first video on the physics of an MRI machine. Whenever we concern ourselves with the physics in an MRI machine, we look at protons almost exclusively. Normally, protons spin along an axis. And what do we mean by that? We mean that if the sphere in this image, if the sphere is the proton, you can imagine a line that goes through the middle of it there. And around that line is how it spins. And this line here is the axis. And the proton normally spins around here. In a body, and whether that is a human body or another object, protons all spin in random directions. And I'll demonstrate what that means here. You can see that all of the protons, they're all spinning around their own axes, but the axes themselves are all pointing in different directions. You can see this one, it's pointing to the left. You can see this one, it's pointing downwards. This one is pointing to the bottom left, and so on and so forth. In a normal body, this is how the protons spin. However, when we enter a magnetic field, protons now have two very important movements. The first is the spin, and second is the precession. I'll go through each of these one by one. So here is, you will recall from 2 slides back, this is what protons are like normally in a normal body. Then we have a spin. So imagine that we now enter a magnetic field, and both of these movements happen simultaneously, but we'll break them down for the sake of understanding. In the spin, this is the same movement that we saw a couple of slides back out in a normal body. However, the movement is now either parallel or anti-parallel to the magnetic field. A parallel movement is when it is low energy. So a low energy proton spins parallel to the magnetic field, and anti-parallel is high energy. This was the original movement that we saw in the beginning, but it's just aligned now, either parallel or anti-parallel. So here, you've now entered a magnetic field, and they're all either, let's say that the magnetic field is pointing upwards, so magnetic field, and you can see that, assuming that this red pointy bit is the direction of the axes, we can see that they are all aligned parallel to the magnetic field. Except, however, this one here, because it is pointing anti-parallel to the magnetic field. And as we have just mentioned, that means it is a high energy proton. And the rest of them are low energy. Now so we've covered the spin. The next movement is precession. And precession can be better characterized or better understood as a wobble, as a very consistent wobble. And this wobble occurs around the direction of the magnetic field. And all protons are aligned in this precession. So here it is. Now, when we enter a magnetic field, you can see that there is this original spinning and spinning and spinning around its own axis, but now there's also this wobble around the magnetic field. So again, if the magnetic field was pointing upwards like that, you can see that, so that's the magnetic field. You can see that here it is wobbling around the magnetic field's direction, and that is the wobble. Importantly, do remember that there is this spin occurring simultaneously as well. So that's the second movement. The spin is around its own axis, and the wobble is around the axis around the direction of the magnetic field. However, in an MRI scan, with just those two movements, there's no change to the system. They just consistently spin and carry out precession. So there's no values that we can record. So we must enact a change in the system so we can begin recording. And that is where something called the radio frequency pulse comes in. The radio frequency pulse is another small magnetic field that we add to the MRI machine that is perpendicular to the original magnetic field. And just for the sake of illustration, the magnetic field, the original magnetic field direction, is also known as, let me make that clearer, is also known as B0. That's just the direction of the original magnetic field. Okay, so just to demonstrate here, if this was the original magnetic field, if this was B0, then we shot a radio frequency pulse at it. The radio frequency pulse would be in the 90 degrees direction. It would be perpendicular. Let's see if I can. The radio frequency pulse would be perpendicular to the original magnetic field. So we'd shoot this at the protons, this radio frequency pulse at the protons, and this pushes the spin out of alignment of the original magnetic field. So if the protons were originally low energy pointing this way, they would, after the radio frequency pulse, point to the right. So this is what the protons look like normally inside a magnetic field. And then you hit them with the radio frequency pulse, and suddenly they're pointing to the right. Remember again that upwards was the original magnetic field. So B0, and that remains B0 because the original magnetic field doesn't change. It's just the protons that point now to the right because that is the direction that they have been zapped with the radio frequency pulse. Recall that low energy protons are parallel to the magnetic field. So if they were low energy originally, they would have been pointing in the direction of the magnetic field. And now that they are pointing, and remember that if they were high energy protons, they would have been pointing away from the B0, the original magnetic field. So that if they were originally pointing here, and now they're pointing to the right, that means they have gained energy. It may not be the highest energy, but they have definitely gained energy. And that is why this process of hitting them with the radio frequency pulse is called excitation. So we excite the protons using the radio frequency pulse. Once the protons have become out of alignment and the radio frequency pulse is removed, the protons return to their low energy spin. So their low energy state, which again was which was pointing in the direction of B0. So to understand how this return to the original precession occurs, this image, if you understand this image, the rest of this video becomes very, very easy to understand. You can see on the top here that we have B0. So this was the direction that the original magnetic field pointed. Then imagine that you hit it with a radio frequency pulse, again perpendicular to the original magnetic field. So radio, we'll label it RF. And then the proton was knocked 90 degrees off its axis, its original axis. So imagine this is the proton here. And this red pointy bit here is the tip of a pencil. So when it's knocked over by this radio frequency pulse, it actually points, the red bit, the pencil bit, points here. So I've colored that red to help you understand. And then the radio frequency pulse is removed. So what it does is it follows this cone-shaped pattern, this overall cone-shaped pattern, back to its original precession. So I'll trace that using yellow here. So imagine the pencil was drawing and it drew this line as it returned to its original state. So it goes round, And on the second rotation, it has a little less energy, so it's a little closer to its original precession. And then a little less energy, and a little less energy, and so on until it reaches its original precession state. And it continues to wobble in that state. So again, here is the excited state of the protons. This is after they have been hit with the radio frequency pulse. And then the radio frequency pulse is removed. And they return back to their original wobble. But there's two types of relaxation that we have just witnessed in this image. And they are called longitudinal relaxation and transverse relaxation. And again, it's very easy to understand this if you understand this image in the bottom right here. Longitudinal relaxation is how relaxed it is in the vertical dimension. So vertically, if we're assuming that after it was excited, it started here, over time, it's actually going upwards. So vertically, or longitudinally, it is increasing. And you can see here, if you follow the shape of this, it actually follows the shape of this graph here in the bottom left. You can see that it increases over time until it hits this plateau. And this plateau is just where it hits the original wobble, or the original precession, the original low energy state, and just continues to rotate around that because it can't lose any more energy than that. The second type of relaxation is called transverse relaxation, and in this image here, it is the horizontal axis. So let's say after the radio frequency pulse, it started here. The next horizontal is actually a little bit inwards, so it's a little towards, so this is 0. So a little closer to 0, and then a little closer to 0, and then a little closer to 0. And it keeps going closer to 0 until, again, it hits its low energy state. So horizontally, it has been decreasing. And that is the graph that we are painting here, in the middle here. Why this is important will become clear in a second. But just for the sake of understanding different notations of MRI, remember that longitudinal relaxation is also called T1 relaxation, and transverse relaxation is called T2 relaxation. So how does the MRI machine pick up these relaxations? Well, there's something called a receiver coil in the MRI machine. The MRI machine, apart from its magnetic field, is just one big receiver coil. What the receiver coil does is it picks up the relaxation time. And the relaxation time is defined as, in simple words, how long it takes the spin to relax back to its low energy state. Understand that different biological matter has consistently different T1 and T2 relaxation times. Consistently different might sound originally like an oxymoron, but what this actually means is that, for example, let's name two organic compounds like fat and muscle will always have different T1/T2 relaxation times. And that's very important to understand. That's how the computer differentiates between different compounds. Again, this T1 or T2 relaxation time depends on the organic composition, which is different in different compounds. And what that means for us in neuroimaging is that tumors, CSF, white matter, and gray matter all of them and other parts of the CNS all appear with different T1 and T2 relaxation times. And that, when the computer converts it into colors or shades for us, that is how the MRI machine differentiates between different parts of the CNS.